You know what's really hard about being a volcano? You spend thousands of years building up this image, cultivating this reputation, and then some upstart comes along and blows you out of the water. Ha ha. It's an evolutionary arms race. But volcanoes don't evolve so much as erupt. And we're hoping to be able to harness the power of supervolcanoes by 2030. No, not their explosive power, their geothermal energy. That's the heat from the Earth's core that these geological giants radiate. It could be our ticket to clean, reliable energy, if we can just figure out how to safely tap into it. We already use geothermal energy on a small scale. Geothermal plants have been producing about 3% of the world's energy for decades. They work similarly to nuclear power plants in that they produce heat through nuclear processes occurring deep within the Earth's crust. But instead of harvesting that heat by splitting atoms, we get it by tapping into leftover heat from the formation of the planet. Basically, geothermal plants are powered by the Earth's crust, kind of. Most of them only run on the steamy breath of regular old volcanoes. They're called hydrothermal power plants. The magma chamber beneath them heats underground water, which becomes steam and spins a turbine, which powers a generator, which presto, produces electricity. There are also enhanced geothermal systems, or EGS, which drill deep into hot rocks. The water pumped into the rock doesn't have to turn to steam. Instead, the hot rock releases heat to the water, which gets carried back to the surface where it drives a turbine. This technology taps into dry steam and hot water reservoirs at depths below 6 kilometers, where temperatures reach around 180 degrees Celsius. Although dry steam systems have been used since the 1970s and EGSs since the 1990s, they're still considered new energy technologies because they haven't been widely adopted yet. Less than 20 countries produce geothermal energy, concentrated mostly in places with lots of volcanic activity like Iceland, New Zealand, the Philippines, and the United States. California alone accounts for 2/3 of all U.S. geothermal production. Geothermal energy has a lot going for it. It's renewable, and unlike solar and wind, it's available day or night. Because it's driven by heat from the core, geothermal power plants aren't affected by weather, meaning they can provide a steady baseload of energy. The downside is that it isn't always accessible in politically stable areas. For instance, the Valley of Tenet's power plant in Nicaragua was shut down during the country's civil war and never reopened. And geothermal plants can face political opposition even when there's no civil war. In 2021, a proposed plant in California's Alvord Desert faced pushback over concerns about induced seismicity. Though the risk of earthquakes from geothermal energy is minimal, researchers have noted that wastewater disposal from enhanced geothermal systems can trigger earthquakes. That was the case in 2009 when wastewater disposal at the Geysers, California's largest geothermal complex, triggered a magnitude 5.7 earthquake. It was felt 100 kilometers away and damaged nearby buildings, but overall, geothermal energy is pretty safe. Even at the highest temperatures found in dry steam reservoirs, the rock containing the magma chamber remains solid. So while we'll certainly need to take precautions, drilling for geothermal power won't unleash molten hell unless we're drilling into the magma chamber itself, which we shouldn't be doing. The thing is, we should be able to drill deeper. Researchers in Germany and France published a feasibility study in 2022, suggesting that we might be able to harvest energy from supervolcanoes like Yellowstone by 2030 if we can just develop new technologies to drill deeper and withstand higher temperatures. As it stands, the deepest geothermal wells top out around 10 kilometers. At that depth, temperatures reach about 200 degrees Celsius. To reach the heat we need to produce energy from a supervolcano, we'd have to go nearly twice as deep, more than 18 kilometers below the surface. These ultra-deep holes would have to survive pressures more than 20 times higher than those found at sea level, and that means temperatures hot enough to melt lead. So how do you drill a hole twice as deep as the deepest hole ever drilled, bore through miles of rock at temperatures hot enough to melt lead? You use a drill bit coated with diamonds. Okay, yeah, it sounds like a fantasy, but diamond-tipped drill bits are actually standard practice in the oil and gas industry, where they're used for directional drilling, which is the process of boring through rock at an angle. Directional drilling is usually done with hydraulic fracturing, or fracking, which involves pumping a mixture of water, sand and chemicals through the drill bit at high pressure. The high pressure breaks up the rock and allows the drill to burrow through it. The sand particles stay in place to keep the hole open while the water flushes away rock cuttings. The trouble is that same fracking process is responsible for many of the environmental concerns surrounding natural gas production. While it's generally safe as long as companies follow best practices, there are cases where fracking has contaminated groundwater supplies. Methane from the frack fluid can also seep into nearby waterways, making its way into the drinking supply. We can mitigate these risks by carefully selecting sites that aren't near active faults or areas vulnerable to flooding. But there will always be a risk whenever you're pumping highly pressurized fluids into the ground. That's why I wouldn't want my house to be built anywhere near a geothermal power plant. But it's not just about drilling deeper and hotter. We'll also need a better material to contain the superheated steam. Luckily, we may have already developed one. In recent tests, engineers pumped supercritical carbon dioxide, or SCCD, through pipes at temperatures reaching 450 degrees Celsius, more than twice the temperature at the deepest geothermal wells currently operating. Unlike water, which turns to steam at 100 degrees Celsius, CO2 stays in a liquid state at much higher temperatures and pressures. It can also withstand higher pressures without breaking down. And if we use recycled CO2, the whole process could be carbon neutral. Finally, we've got to consider the risk of volcanic eruptions. The thing is, it's really unlikely that we'd trigger an eruption. Just because we're tapping into a volcano doesn't mean we're tapping into a magma chamber. There are plenty of dormant volcanoes that have cooled off for good. So even if we're drilling into the right volcano, we probably won't cause an eruption. But let's say we do accidentally awaken a slumbering giant. Well, we won't have to worry about toxic ash clouds or lava flows. That's because the site of the world's most recent super eruption, Yellowstone National Park, is largely protected. The U.S. Geological Survey monitors seismic activity at the park daily and issues warnings when there are signs of increased unrest. An eruption at Yellowstone would be bad news for a lot of reasons, but the worst effects would be felt by the people living closest to it. So, provided we exercise extreme caution and include careful monitoring in our safety protocols, we should be okay. Plus, the likelihood of us triggering an eruption in the first place is extremely low. In fact, scientists think that geothermal energy could help prevent eruptions. One theory suggests that magma chambers are full of dissolved gases that escape as the magma chamber approaches the surface. Once those gases reach a critical threshold, the magma becomes less dense. It rises to the surface, triggering an eruption. If we can pump cold water into a magma chamber, we can keep the gas levels low enough to prevent an eruption. In theory, we could even suppress ongoing eruptions by injecting water into the vent. Scientists tested this method at Mount Ibu in Indonesia. By pumping cold water into the volcano, they were able to lower temperatures and reduce volcanic activity. It's a bold plan, but if it works, we'll finally be able to harness the immense power of supervolcanoes, which begs the question, why hasn't anyone thought of this before? Well, it's hard to come by drilling permits for places like Yellowstone because the area is mostly protected. Plus, given how rare supervolcano eruptions are, it probably didn't seem worth it. So while humans have known about geothermal energy for centuries, our attempts to harness it have been pretty limited. We started with hot springs and eventually progressed to harnessing the heat from smaller volcanoes. But it's taken until now to develop the technology needed to reach supervolcanoes. And the truth is, we probably couldn't have done it without the oil and gas industry. Advances in drilling techniques and materials were developed to extract fossil fuels, but they can also be used for good. We just have to get there first. And thank you for watching.